Hello all. So in today's video, we'll learn about how to find inverses of a matrix if they exist. In the previous videos, we learned about matrix multiplication, matrix addition, subtraction, and some basic operations that are useful for our future learning in linear algebra. In this video, let's introduce the concept of matrix inverse and how to calculate matrix inverses. So emphasis on the fact that if A is a square matrix, matrix is invertible if and only if it is a square matrix. A is a square matrix, then A inverse is the matrix such that this equation is satisfied. So when you multiply A by its inverse, it will be commutative and both products will equal to the identity matrix. And I've already introduced identity matrix in one of the introduction videos. Now, this A inverse might not always exist, but if it does, if this equation holds, then we say that A to the power of -1 is the inverse of matrix A, where A is a square matrix. Now, for 2 by 2 square matrices, finding inverses is a really straightforward technique. For example, this will be the general process. So if A is this 2 by 2 matrix, A, B, and C, D are real numbers or complex numbers depending on the context of the question, such that A times D minus B times C is not equal to 0, then A inverse exists, then A inverse exists. And we can calculate A inverse easily by multiplying this matrix by the reciprocal of AD minus BC. In future videos, you'll learn about the concept called determinants, and there you'll learn that this value right here, the AD negative BC, is the determinant of this 2 by 2 matrix. But for now, we can just apply this straightforward formula for any 2 by 2 matrix. So you can see that I've interchanged A and D are interchanged, and I've changed signs on B and C. Let's make sure that we understand this process by figuring out an example. So I have a 2 by 2 matrix, A equals 1, 2, 3, 4, and I have to find A inverse. Typical question and exam will look like this. You have to find A inverse if it exists. So first I will write down my A, B, C, D, compare it with the 2 by 2 matrix, the generalized form above. And now I calculate the AD minus BC value. AD minus BC turns out to be 4, -6, which is -2. It's not equal to 0. Hence, A inverse exists. And once we know that A inverse exists, we just apply all the values and get the inverse. So A inverse will equal to 1 over -2 multiplied. Now I've interchanged A and D. So 1 and 4 are interchanged to 4 and 1. And I've changed signs on C and D. I'm going to multiply this scalar by each entry in the matrix, and there you go. This is the resultant inverse. And straightforward. You can also verify your answer. You can double check if you are not allowed a calculator in exams. You can always multiply two matrices, and if the resultant product is identity, then you have the right inverse. If it's not identity, then you made an error somewhere. So what happens if a matrix is square but not 2 by 2? If it's of higher order, how do we find the inverse? The first technique that you're going to learn in this video will use Guass-Jordan elimination. There are other ways to find the inverse of a square matrix of order higher than 2. We will learn about those methods in future videos. So How do I apply Gauss-Jordan elimination to find the inverse of matrices which are of order greater than 2? We will follow the following steps. We will set up the augmented matrix of A with the same order identity matrix, where I is the identity matrix of the same size as A, and we apply Gauss-Jordan elimination on A. And how do we check if A inverse exists? We will see that if the matrix on the left-hand side is identity, then the matrix on the right-hand side is A inverse. However, A inverse do not always exist. So if you cannot get a identity matrix on the left-hand side, then we conclude that A has no inverse. We will do an example of each case in this video. Let's start with a 3x3 matrix. And spoiler alert, this matrix does have an inverse. But I want to use Gauss-Jordan elimination to find the inverse of A. So, step 1, I'm going to set up the augmented matrix A. You can use a slash here, a straight line, I. And I here is going to be of size 3 because I have a 3x3 matrix. And I will perform the row reduction on A. Now you have to keep in mind whatever operation you're doing on the left-hand side, you have to apply that consistent operation on the identity matrix on the right-hand side. So I have A here. All of you must be familiar with the Gauss-Jordan elimination process. You can watch a video, a previous video, to practice a few problems. I begin with the leftmost corner, and I need to make this entry a 1. Now, to make this entry a 1, I will need to divide row 1 by 1/3. Now, just be careful. Whatever operation you're doing on this side, you have to do the same operation on the left-hand side. So consider this a big matrix, a big 3x6 matrix, and you're doing all the operations. Don't forget this right-hand side matrix. So I'm multiplying row 1 by 1/3, and this is the resultant output. Now I have my pivot 1 in the leftmost corner. I need to make everything below this 1 a 0. So I need to perform 2 operations here. I need to make changes in R2 and make changes in R3. In R2, I'm going to add 2 times R1, and that would give me the resultant 0. And in R3, I will add a negative 4 times of R1, and that would give me the desired 0. And the same operations I'm going to be applying on this side. Once you do your math, take a minute, pause the video, and see if you have the same answer as me. Now, I have 1 here, I have 0 below it, so this column is done. To get the RREF, I need to move on to the next column, and now I need to make this guy a 1. Now you'll notice that I have a 0 in place of the pivot entry, but I have a non-zero entry right below it. So think about it. What operation can I apply to get a 1 here in the pivot entry? In cases like this, we usually avoid adding or subtracting rows or multiple of rows or scalar multiples of rows. We should do the easy route, that is interchange 2 rows. So I'm gonna interchange row 2 and row 3 to get the non-zero entry in the desired pivot place, right? And now I have a non-zero -3 in my pivot position. Then I'm gonna continue with my steps of RREF. So I need to make this -3 a 1. How do I do that? I divide R2 by, I multiply R2 by a -1/3. This is just technical language. Basically what you're doing is you're dividing row 2 by -3. Now in this in this step, I've done one way ahead, and I see a 2 in the last pivot position, and we know that we need to make this 2 a 1. So instead of making 2 row operations separately, I've combined them into one step. Because you see, row 2 and row 3 are independent of each other, right? We're not using row 2, we're not adding any scalar multiple of row 2 to row 3, right? They are independent rows, so I can apply a row operation to both of these rows in one step for cases like this. Important step. Okay, now I have a pivot entry here, I have a pivot entry here, which is 1, and in the same step, I get a pivot entry here. Now, whatever operation I'm performing on the left-hand side, I'm going to continue with that operation on the right-hand side. Same thing here, I'm going to divide everything here by 2. And this is the resulting matrix. Take a minute, do the math, and see if you have the same answer. Do not forget the matrix of the right-hand side whenever you're doing your row reduction for finding the inverses. Now, the 2 last steps, I need to make this entry above this one a 0, and I have to make these 2 entries zeros. So I'm going to pick there's no right order of steps here. It's up to you which entry you want to make 0 first. I picked column 3, and I'm making the -1 a 0. So I'm going to add R1 plus R3. I'm going to make a 3 a 0. So I'm going to add R2 plus a -3 times R3 to that column. And there we go. These 2 entries are the desired 0 that we needed. You see, it's looking very close to identity, but not yet. I have one last non-zero entry that needs to be turned. Last operation that I need to perform, I'm going to add a -2 multiple of R2 to make this to a 0. And that gives me the resultant identity on the right-hand side. And this is what we wanted. And based on the steps above, if you have obtained an identity matrix on your right-hand side, then on your left-hand side, then the matrix on the right-hand side is going to be your A inverse. So we can transform A into the identity matrix, hence A inverse exists, and A inverse equals to this 3x3 matrix. You can also verify, and how do I verify that this is the correct inverse? You all know how to multiply 2 matrices. Multiply A with A inverse and see if you got identity back. You may not always be asked to verify your answers in exam. It's good practice, especially if you don't have calculators. You cannot verify your answers easily, right? Now, remember when I said that not every square matrix is invertible? We could easily tell for a 2x2 matrix just by finding the AD minus BC value. How do I check for a 3x3 or higher order square matrix to see if it has no inverse? We will construct the augmented matrix here, A slash I. I'm considering this example right here, A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Try constructing the augmented matrix and start row reducing A. What you will notice is you will end up with a row entirely consisting of zeros. When you end up with a row full of zeros, right? What happens? There is no way you can make this matrix an identity matrix. There is no way LHS, no row operation can make this left-hand side an identity matrix, can be reduced to identity matrix, right? And for cases like this, we say that A inverse does not exist. Now, this may look like it's a long process just to find out that A inverse does not exist. We will learn shortcuts by using determinants in next video. See you in the next video.